All right. And we'll still got people that are likely to be walking in late, but we've got a lot to cover today. So that today's lab makes sense without a full lecture at the beginning of lab as well. So we're gonna go ahead and get started. We only have two more lectures of new material. Get today where we're going to talk about reaction types, and then we're going to focus in on one of those reaction types, acid-base reactions, for our final calculation skills of the quarter. And then on Wednesday, we're going to talk about other reaction types and how we can tell what type of reaction something is, because that will be some of the points on your final. Will be for those stoichiometry problems. I'll say, okay, here's a reaction. What type of reaction is it? And that'll be some of the points associated with those problems. And then next Monday is review session. Because it's officially not the beginning of the finals we get it. I know I mentioned that last week, but just to reiterate, our final exam is scheduled for Wednesday, and we will meet for a review session for anybody who wants to come on Monday at our regular lecture time. So a week from now, exactly. And the review will basically be after you've spent some time with the practice test. What do you want to go over? Do you want to do practice with Lewis dot structures? Do you want to do stoichiometry practice? Do you want to talk about some of the conceptual stuff or nomenclature stuff? I'm just going to answer questions as you all ask them for 2 hours on Monday. And then we won't meet for lab next week. So next week we have no lab. So you have those extra 3 hours. I'll be around for the lab time slots. If you want to come and use that as extra office hours to ask me questions. But I will, since we're not officially scheduled to meet, if you're going to come in during the lab time slots for office hours, let me know ahead of time so I make sure that I'm around and not in a meeting or something. I know on Thursday and Friday of next week I'm on a hiring committee, so I'm going to be gone all of Thursday and Friday. You have your test with me on Wednesday, so it shouldn't affect you, but there are other meetings and stuff that crop up during finals week. So if you want to use that lab time, I would be more than willing to hang out with you during lab time and talk about that stuff. It's more fun than doing committee meetings anyway. But you just gotta let me know, make sure I'm there. All right. Today we're going to talk about the first half of class. We're going to spend on types of chemical reactions and try and figure out like what are the sort of broad classes of different types of chemical reactions. And then we're going to talk about these two types today, precipitation and acid-base reactions that share a lot of similar properties. At least once you get used to how to think about this. It might not seem that similar on the surface yet, but we'll get there. And then today's lab, we're going to do some practice with acid-base reactions. We'll do a titration where we're looking at different pHs. So we'll spend some time talking about pH a little bit today too. All right. So if you look up a textbook for this class, there's 10 major textbooks for this class to choose from that are all pretty common. The problem is that they all have different definitions of what the different reaction types are. They all kind of look like this, where they're talking about, oh, you can either have synthesis or you can have decomposition. Synthesis is when you take two small things and make something big. Decomposition is the opposite. Sometimes they'll say single replacement versus double replacement. I don't like these definitions because they're not very well defined and because they're not universal. If you start looking at other areas in a different textbook, you get something that looks like this, chemical reactions, and then it just splits it into 4 subcategories immediately off the bat. But those don't look like single replacement or double replacement or synthesis or decomposition. This is just a different way of organizing things. But it's from a textbook that's the same level. It's for the same class. So it doesn't really make a whole lot of sense. If you keep looking, you get, okay, well, everything comes down to it's either addition, decomposition, or neutralization. Or you find if you look into an organic chemistry textbook, you get things can be nucleophilic, electrophilic, or radical, and they can be substitution, addition, or elimination reactions. This is all true also. So what the point I'm trying to make here is that depending on what area you go into, every different scientific field has its own way of classifying chemical reactions. That's going to be more relevant to what you're studying. I think there's one. Yeah, and if you go to biochemistry, they classify it based on what the type of reaction looks like, but also what type of enzyme is catalyzing the reaction. It doesn't really make sense to learn hard and fast, these are the only 4 reaction types. Because depending on what your context is, there's going to be other reaction types or other ways of classifying the same reactions. So when I started teaching this class a long time ago, I started going through this and I wasn't happy with any of those other ones. So I basically broke it down to the simplest version you can have of how we classify reactions in sort of a flowchart way. Either when a reaction happens, you transfer electrons between atoms, aka charges change, or they don't. So at its most basic, all of those other types of reaction classifications are starting from the point of view of either electrons transfer or they don't. And so this is going to be our primary way of distinguishing reactions. Right? So our definition of electrons changing hands, we say electrons are transferred between atoms. We call that an oxidation reduction reaction. Which the shorthand for that is redox. Redox stands for reduction oxidation. Either things are a redox reaction or they're not. And I don't, like I said, I kind of came up with this as the most broad way of looking at this. You could just say it's a non-redox reaction. You could say it's a rearrangement reaction. I've seen people call it a complexation reaction. Basically, if it's a rearrangement reaction or a non-redox reaction, it just basically means everything is keeping the same charge, the same general identification, but they're just rearranging the pieces. So rearrangement reactions are more like taking apart a Lego model and rebuilding something else. It's still all the same pieces, even though it might look different. Versus our redox reactions, we're totally fundamentally changing the identity of the pieces. And so redox reactions are more like if you took your Lego model and you dissolved it in acetone and then cast something new with the plastic. So it's really these tend to be harder to reverse, but you are actually getting new ions, new compounds as a result, as opposed to just rearranging the pieces you already have. All right, so how do we tell which of these is which? There we go. If it's a non-redox reaction, if it's a rearrangement reaction, your atomic charges aren't going to change. So if you started with something with calcium ion that has a +2 charge, it's still calcium ion with the +2 charge at the end. It might just be attached to a different anion, but it's still going to have that overall charge to it. Right? And I think I actually got these backwards order from the way that I'm going to talk about them. The other type, so the first type of rearrangement reaction is what we call an acid-base reaction. And the easiest way to think about acid-base reactions is we're moving a single H+ ion from one compound to another. So for instance, if we started with, say, HCl, aqueous, we know how to name that, right? What is that one? Hydrochloric acid. We put hydrochloric acid with, we'll do the classic example, sodium hydroxide. One of the things that can happen is if this HCl can give away an H plus to something else, it can become more stable. So the net reaction in this case is if you put a hydroxide with an acid, the acid gives away its H plus to the hydroxide. What do you get when you put an H plus and an OH minus together? H2O, and the charges add up to 0, right? Because we had a +1 and a -1. So if we stick an H plus onto a hydroxide, we get H2O with no charge. So by just moving a single H plus, we get a new compound. And then what's left over? Well, we had sodium ions and we had chloride ions. So we still have sodium ions and chloride ions. When it's water dissolved in water, we don't say it's aqueous. You can't have aqueous water. Something can't be dissolved within itself. So we just write it as we're making liquid water because it joins the rest of the water molecules in the solution. Right, so most of your acid-base reactions, all of your acid-base reactions for this class are going to look something like this. Something has an H plus, something else has a negative charge. We're not going to really, you can stick an H plus onto something neutral. If whatever you have is positive though, you're not going to stick an H plus on it because positives repel other positives, right? So all we're really doing is moving an H plus from one thing to another. Nothing is really changing charge here. Our sodium ion still a sodium ion, a chloride ion still a chloride ion. It looks like the H plus changed charge and the oxygen and the hydroxide changed charge because we don't have any hydroxide anymore. So let's talk about that. How do we decide for a covalent compound what the charges on all the atoms are? Right, so the way we look at this is what's called oxidation state. So for oxidation states, it's basically an invented way of finding a charge on covalent compounds. If you have covalent bonds, we don't really have a charge between those covalent bonds. But that makes it hard to tell whether any electrons change hands sometimes. So oxidation state, we're just going to treat everything like it's an ionic bond. So anything that's already an ionic compound, like sodium chloride, we can look at this and we know what the charge is on each of those ions, right? Because we have our periodic table, we know that sodium is a +1, and we know that chloride is a -1. But what about hydroxide? Well, let's start with an easier one. Let's do water first. If we have water, we can't really say that the oxygen has a charge and the hydrogen has a charge since it's a covalent compound. And covalent means that they're sharing electrons. That's how we first started talking about covalent compounds, right? But then we immediately got into it and said, well, there's this thing called electronegativity because the electrons don't get shared evenly, right? So what we do with covalent compounds, if we want to know the oxidation states, we just say, okay, we're going to treat it like it's an ionic compound. And whatever is most electronegative gets first dibs at the electrons. So when oxygen is an ion, what's its charge when it's most stable? -2, good. And it's more electronegative than the hydrogen, so it gets first dibs on the electrons. So what does the charge have to be on the hydrogen if the overall charge adds up to 0? There's 2 hydrogens and they're both +1, right? So really just treating it like it's an ionic compound. We've got some practice with that now for figuring out charges, right? What about hydroxide? What gets first dibs on the electrons? What's most electronegative out of oxygen and hydrogen? It would still be oxygen. So oxygen's still -2. Basically, unless oxygen is bound to another oxygen or to a fluorine, oxygen's always going to be -2. It's the second most electronegative element that we have. Right? Fluorine is the most electronegative, and then oxygen, and then nitrogen and chlorine were pretty strongly electronegative too. So oxygen's almost always going to be a -2. What does the charge have to be on the hydrogen for it to add up to a total of -1? It's still got to be a +1, right? So if I go back to the same reaction that we started with here, I'm going to rewrite it so we can look at everything here. HCl plus NaOH turns to H2O and NaCl. We've already talked about the sodiums and the chlorides. They don't really change, right? Their oxidation states are still, chloride is -1 here. It's still -1. Sodium is a +1 here. It's still +1. The hydrogen here has to be what? It's got to balance out the charge on the chloride, right? So it's still got to be a +1. We just did hydroxide, but we could do the same steps. Oxygen's the most electronegative thing here, right? So it gets first dibs, it's -2, which means this hydrogen also has to be a +4. Right? Because all three of these charges still have to add up to 0. Hydroxide is going to have the same oxidation states no matter what its counter ion is, no matter what the metal ion is. This oxygen's still -2 on this side, right? We just did the oxidation states for water. Oxygen gets first dibs, so it's still -2. There's two hydrogens that both have to add up to a total of -2 to cancel things out, for a total of +2. That's a lot of seemingly random numbers that I threw up there really quickly. But if we look at it, nothing changed oxidation states. Everything that was a +1 is still a +1. If it was -1, it's still a -1. If it was -2, it's still a -2. That's how we know it's not a redox reaction. Nothing changed charges. Even though it looks weird to say, oh, well, I had an H plus and a hydroxide, and now they're water. Seems like charges changed, right? But not on the individual atoms. The individual atoms stayed the same oxidation state when it was hydroxide or water. So if nothing changes oxidation state, it's not a redox reaction. All right, let's do one more. Just to see another example of what an acid-base reaction can look like. What's an example? Let's somebody give me any acid. Anything we would name as an acid from our nomenclature packet.
Hydrofluoric acid.
Hydrofluoric. Good. Hydrofluoric acid looked like this, right? You put hydrofluoric acid with, this is a molecule we haven't learned how to name yet. Does anybody know what that one is? Gets used in cleaning products a lot. Close. Ammonium is when it had the +1 charge, right? That's what we're going to make. This is ammonia. So if you buy ammonia from the hardware store as a cleaning supply, you're getting a solution of aqueous ammonia. When you put it with an acid, the NH3 can take the extra H plus. So we make NH4 plus, which is one of our polyatomic ions we have memorized, right? That's ammonium now. Plus which sometimes we would put these together and write ammonium fluoride as our final product. Either way, though, what's the most electronegative element out of these two? Fluorine. If fluorine's involved, fluorine's always the most electronegative. It is the most electronegative element, period, full stop. So fluorine always gets first dibs. The only time fluorine is not a -1 is when fluorine's attached to another fluorine. So then the hydrogen still has to be +1. On this side, nitrogen's more electronegative than hydrogen, right? So check your periodic table. Nitrogen wants to gain 3 electrons to be stable, right? So if it got first dibs at the electrons, it's a -3. Which means all 3 hydrogens have to be a +1 to make it add up to 0. Our oxidation states have to add up to the overall charge of the molecule. If our molecule is neutral, our oxidation states have to add up to 0. Ammonium looks a little different, but it's still nitrogen and hydrogen, right? So nitrogen still gets first dibs. So it's still -3. Each of those hydrogens is still a +1 because they have to add up to an overall +1 charge. And our fluoride is still -1 over here. So once again, nothing changed before and after. All that happened is we took an H plus from the hydrofluoric acid and we stuck it onto something else. For now, I'm not going to ask you to complete these equations. Actually, for this class is less about you predicting what the products are going to be and more just recognizing what the reaction is. Right? So I'm not going to have you fill out the products for this class. Right? What I do want you to be able to do is recognize, okay, there's a reaction. The only thing that happened is I moved an H plus, therefore it's an acid-base reaction. All right, precipitation reactions are arguably even easier to recognize. I won't say acid-base reactions are always easy to recognize. When you know what you're looking for, they're not too bad, but it takes a lot of practice to be able to say, oh, ammonium and ammonia, that's the same molecule with an extra H plus. That takes some practice. So we'll work on that. Precipitation reactions are even easier because really nothing changes. In a precipitation reaction, all that happens is you mix different ions together in a way that no longer stays dissolved in water. Right? So precipitation reactions always look the same. You mix 2 aqueous solutions and you make a solid. Not only 2 aqueous solutions, typically, especially for this class for now, 2 aqueous ionic solutions. Right? So technically precipitation happens anytime something goes from being dissolved to being a solid. And that's, you hear the term precipitation a lot when it comes to meteorology, right? That's when water is coming out of being dissolved in the atmosphere and turning into a solid or a liquid. So it's similar. It was part of the solution and then conditions changed so that the water no longer stays dissolved in the atmosphere based on temperature or based on humidity or based on lots of other things. In this case, It's always going to be two aqueous ionic solutions, and when you mix them, you make a solid. Right? So, for example, silver nitrate dissolves in water pretty well, as does sodium chloride, salt. However, when you put them together, we get different combinations. So silver nitrate stays dissolved, sodium chloride stays dissolved, but as soon as we mix these ions together, we get new combinations. For instance, we could put silver with chloride, or we could put sodium with nitrate. Do we know if either of those are going to stay dissolved? Do you know right now if those will stay dissolved in water? I don't expect you to. We don't really have a good way of knowing that off the top of your head. You haven't taken your chemistry. So basically what we do is we have a list of rules to say, okay, these combination of ions will stay dissolved, are soluble in water. And these combinations of ions are mostly insoluble. They'll mostly turn into a solid. In this case, I happen to know silver chloride, when you mix those two together, it forms a solid. It won't stay dissolved. But sodium nitrate does. Right? So any precipitation reaction is going to look like this. Start with two ionic aqueous reactants. And when you mix them together, if a reaction happens, you're going to make a solid. Right? And so knowing, skip around a second. This table down here that I just pulled straight from Wikipedia is an example of what we call solubility rules. Solubility rules basically say, okay, group one, aka column one on the periodic table, is always soluble. So with one exception, lithium phosphate doesn't dissolve in water. Every other ionic compound you could make with column one or with ammonia will stay dissolved no matter what. Nitrates dissolve in water. There's no exceptions after that. So nitrates will stay aqueous no matter what. On the other hand, carbonates are almost all insoluble. If you put carbonate with a positive charge that's not group one or ammonia or a urea-based compound, it will stay dissolved. Or sorry, it will not stay dissolved. Insoluble means it'll form a solid. Insoluble, soluble means it dissolves in solution. Insoluble means it forms the solid. So what does that look like for a carbonate? Means if I take, we'll use sodium carbonate. Plus calcium chloride. If I let sodium carbonate and calcium chloride react together, sodium is soluble no matter what. So what are our new combinations, what we could make? We can't put the sodium with the calcium because those are both positively charged. So that's not going to happen. That's not how we do ionic compounds, right? So the only other option that we could put the sodium with is with the chloride. So we could make sodium chloride. we don't know without checking those solubility rules, is it going to be aqueous or solid though? Except where is sodium on the periodic table? Group 1A, column 1, which means sodium is soluble no matter what. So what state is it going to be in? Is it going to be solid, liquid, gas, or aqueous? It's going to stay aqueous. And now our other option is calcium carbonate. So we go look at our solubility rules, which I will give you on the test. I don't think I actually have you predicting reaction versus no reaction, but if it was part of the test, I would just give you the solubility rules. I don't expect you to memorize them at this stage. And you would just say, okay, well, does calcium carbonate stay dissolved or not? Or is it insoluble? Because carbonates were on our list of mostly insoluble, and calcium was not one of the exceptions, we know that this is going to form a solid. So what do we do with that? At the very least, what we want to be able to do is recognize that if I write this whole reaction out, that it's what we call a precipitation reaction. Right? Again, the more time you spend on this, the more you start to remember, oh, I don't have the entire solubility rules table memorized, but I know some of the common ones. I know that chlorides are almost all soluble with 4 exceptions, I think, one of which is silver. But even some of the other ones, I would go back and double check. Sulfites are mostly insoluble with a couple exceptions. Phosphates are mostly insoluble with a couple exceptions. And then an exception to the exception. It does take some practice reading these, but this is going to tell you what happens when you mix ionic compounds together, when you mix different solutions together. And this is an example, trying to, anyway, I think I have to get rid of the eraser. Not gonna let me click on it in the back end. We will just search it up by hand real quick. These are some of the reactions that used to be the reason why alchemy was considered like a magic practice, because you can basically, if you mix a lead solution with an iodide solution, says it's full.
Hello, everyone. Today we will conduct a very beautiful experiment.
Man, how far AI voices have come. So, I won't go full screen, but basically we start with 2 colorless solutions, and when you mix them, you get this yellow powder forming, which almost looks kind of liquidy, but it is a solid. It settles out eventually. If you swirl it up, it looks like that. And you can actually get it to, if you sit right at the edge of how soluble that compound is, you can get it to redissolve. And if you get it to crystallize really slowly, you start getting these larger flakes forming that all do kind of look like gold. And considering this was made from lead iodide, this was one of the classic examples of, we are really close to turning lead into gold, like the alchemists would have said, to try and keep their job back in the Dark Ages. Because if you have no knowledge of chemistry and somebody tells you, I took lead and I made this solution, I dissolved the lead into the solution, when I mix it, look what happens. looks kind of golden, right? So this was sort of the like, we're on the right track. They weren't on the right track, but they were able to make it seem like that. And then they could take this and make it redissolve again. So most precipitation reactions look something like that, where you mix, they're not all that colorful. More often than not, you make a white powder instead of something like this that has these shiny flakes to it. But for the most part, if you mix two colorless, clear solutions together and then it gets cloudy, that was a precipitation reaction of some sort. You made something solid, and that's why it got cloudy. All right. So a couple more. Let's the really broad. Definition of it's either redox or it's not. Our two main categories of non-redox reactions, of rearrangement reactions, are it's either acid-base or it's precipitation. If it's precipitation, you can clearly see you have all the same ions before and after. If it's acid-base, it's a little trickier because what looked like a hydroxide before might look like a water now. But if we look at those oxidation states, we can see nothing's changing charge. So let's look at the opposite case. These redox reactions. Redox reactions, if it's a metal redox reaction, they're actually really easy to recognize. Metal redox reactions are easy to recognize because you can just look at the individual charges and see they're changing. If a metal ion is changing charge, it's a redox reaction, period. You don't even, just by looking at the charge, we know that the oxidation state's changing. So I'll reiterate, for ionic compounds, oxidation state is the same as charge. Right, so sodium goes from an oxidation state of 0 to an oxidation state of +1. It changed oxidation state. Therefore, this is a redox reaction. And on the flip side, the zinc goes from +2 oxidation state to a 0 oxidation state. Right, so as soon as you can see the charge is changing, you can write redox. Combustion reactions are also redox. We use these as examples a lot for our balancing practice, right? It's really easy for me to make up new combustion reactions because they always look the same. Combustion reactions always start from a hydrocarbon plus oxygen, and they always make CO2 and water. Right? No matter what the starting material is, it's always plus oxygen makes CO2 and water. You see that? And I ask the reaction type, you just write combustion. Right? So in my mind, those are the easiest to recognize because they always make the same products. Right? Why would we classify those as, we'll rewrite that one larger here, as redox? Well, let's look at the oxidation states. We've already looked at water, so we can start with water first. Might as well, right? What's most electronegative out of H2O? Oxygen. Oxygen gets first dibs. It's going to be -2. Hydrogens, there's 2 of them. They're each +1. How about CO2? What's most electronegative? Oxygen, and there's 2 of them. So the carbon has to be +4. Let's look at the oxygen over here. I didn't finish balancing this properly, but that doesn't matter for oxidation states. What's the oxidation state for oxygen bound to itself? Can it be -2? Can't have an oxygen be -2. These oxygens are equivalent to each other, right? So they have to have equal charges. Zero. Anything in its elemental state is going to have an oxidation state of 0. We can't say that one oxygen is, if we had the Lewis dot structure, it looks like this, right? Oxygen double bound to oxygen. It was one of the first examples of Lewis dot structures we looked at. We can't say that one oxygen has more of a negative charge than the other. So we can't say -2 and +2 or something like that. If we have two identical atoms, they have to have the same charge on them. The only number 2 times x equals 0, or x plus x equals 0, the only way you can solve that is if x is 0. So that means our oxidation state for the oxygen has to be 0. So what does that mean? It means that our oxygen changed oxidation states. It went from a 0 to -2. No matter which oxygen it is, it started at 0 and it ended. All of our oxygens on this side are all -2, right? So the oxidation state had to change. Let's look at methane here. What's more electronegative out of carbon and hydrogen? Carbon just barely, right? So that means carbon gets first dibs. How many electrons does carbon need to gain to be stable? 4. So that would give it a -4 charge, which makes all of our hydrogens +1 again. So our hydrogens didn't change oxidation state, but our oxygen did, and our carbon did. All right, so let's define a couple more terms when it comes to these redox reactions. The full name of these redox reactions was oxidation reduction. It's called oxidation reduction because 2 things have to happen. Oxidation is when something loses an electron. When something loses an electron, that electron has to go somewhere. We don't just have random electrons flying around. The only time that happens is in a plasma. For the most part, if something loses an electron, something else has to take the electron. So these 2 processes always have to happen together. If oxidation is loss of electron, reduction is gain of electron. Which actually makes a pretty convenient way to memorize this. Way to recall this is oil rig. Oil rig stands for oxidation is loss, reduction is gain. The other way that you can remember this is Leo the lion says grr. Leo says grr. Leo stands for losing electrons is oxidation. And grr is gaining electrons is reduction. This is, we can blame Ben Franklin again for getting the charges wrong at the very beginning. When you gain an electron, your charge goes down. So that's where the word reduction comes from. The charge is reduced when you gain an electron. So either of those, oil rig, Leo says Gur, you just think about the charges. Reduction must mean I gained an electron because the charge is reduced. So with that in mind, what atoms are being oxidized up here? Oxidation is loss of electrons. So what should happen to the charges, the oxidation states? They should go up, exactly. So what on here had its charge increase? And we will go from left to right. So the carbon is oxidized. What's reduced? The oxygen is being reduced. It goes from being 0 to being -2. So it gained electrons to do that. All right, so then there's a couple pages with practice for oxidation states as well. We're gonna look, we'll do the bottom ones here real quick. Let's look at the phosphorus-based compounds. We'll start with the one that's just pure ionic, because that's the easiest one to do. What's the oxidation state on, well, what's most electronegative between calcium and phosphorus? Phosphorus. Anytime you've got a metal and a non-metal, basically our dividing line between metals and non-metals is based on the electronegativity. Your non-metal is always going to be more electronegative than your metal. I can't think of a single exception to that. But I'm also not looking at that sheet. So if you see an exception to that, let me know. But for the most part, non-metal is going to be more electronegative. So your non-metal is always going to be negative. So phosphorus here, it has to be what? -3, and there's 2 of them. So calcium is, and there's 3 of them, right? So basically this is just reframing the same way we come up with these formulas in the first place for ionic compounds. We've already been doing this. We just reframed it as oxidation state. What about PCl3? What's more electronegative? Chlorine is one of our big 4, right? One of the Mount Rushmore of electronegativity. So chlorine gets first dibs. There's 3 of them, and they're all -1. So the phosphorus has to be +3. This one looks weird. This one doesn't look like it matches with the octet rule. Turns out when you get to the 3rd row of the periodic table, that octet rule of just get to 8 valence electrons kind of falls apart sometimes. So this is a real compound. PCl5 is a real thing. I haven't taught you how to figure out the Vesper geometry or do the Lewis-Dot structure for that yet. And that's fine. We're not going to get to it in this class. When you take Gen Chem, you'll see that it does still make sense. PCl5, chlorine is still more electronegative, right? So it's -1. And there's 5 of them. So the phosphorus has to be +5. If you look at where phosphorus is on the periodic table, does a +3 and a +5 charge make sense based on the orbitals? Well, it's a non-metal, so we're used to thinking of it trying to gain electrons. But phosphorus has 3 valence electrons in the p orbital, right? It's got a total of 5 valence electrons, which makes the +5 make sense. It can either gain 3 electrons to become a -3, or it can give up 5 electrons to be a +5, which corresponds with emptying its valence shell, right? +3 is a little bit weirder, but it corresponds with emptying the p orbital and it's still having a full s orbital. So it does still kind of make sense. You can't make PCl4. It doesn't exist. You can make PCl3 and PCl5 though, because that's what the orbitals show you is reasonable for a phosphorus. Right, so usually your oxidation states are going to match with something that makes sense for an electron configuration, either gaining electrons to fill everything up or losing electrons to empty things out. So let me clear this. You know. Or I would just do CH4. We already looked at CH4, so we did that one once already. What's the charge going to be on the carbon? -4. And then the hydrogens have to add up to +4. There's 4 of them. Can hydrogen ever be +2? Why not, Brooke? It's the first element, which means it only has how many electrons when it's neutral? It only has 1 electron when it's neutral. If it loses 1 electron and becomes +1, you can't lose something you don't have. So it can't become +2 because it only has 1 proton in the nucleus anyway. When it loses all of its electrons, it's a +1. That's where it stops. So if you ever get hydrogen as a +2, you did something wrong. Hydrogen can be a 0 if it's neutral, like that. What about sodium hydride? What's more electronegative out of sodium and hydrogen? For the first time, hydrogen's more electronegative now. When you put a hydrogen on a metal, the hydrogen actually gets first dibs finally. What's the charge going to be on a stable, excuse me, on a stable hydride? -1, because it only needs to gain 1 electron to fill its valence shell, right? And sodium, it's going to be a +1. So hydrogen can be +1, it can be 0, or it can be -1, but those are your only choices for hydrogen, which is going to help us up here when we're limited, when we kind of have a couple different things happening. So how about for formaldehyde here? Sometimes it's written as CH2O. You're in an OChem class. What's most electronegative? So it's going to be -2. Then we have one that's in the middle. If we have 3 different compounds, it's usually a good idea to start at the ends and work your way in. We already figured out oxygen's the most electronegative. We know that hydrogen is the least electronegative. So hydrogen has the fewest electrons. So what's the charge going to be on the hydrogen? Positive, and it can only be, if it's positive, it's got to be a +1. And there's 2 of them. That means carbon's got an oxidation state of 0 in this case. Right, so the way to do it when you've got 3 different compounds or 3 different elements, most electronegative, least electronegative, and then the middle one has to be whatever's left. So most electronegative, still oxygen, still -2. And there's 3 of them now. Two hydrogens, they're the least electronegative and they can only be a +1. So we've got +2 and a -6, which gets us to an overall -4. So the carbon has to be +4. And so this is one of the reasons why carbon is so useful in our bodies, why living organisms are all the living organisms we're aware of are based around carbon. Partly because carbon actually has a lot of different stable oxidation states. Most other compounds on the, or elements on the periodic table only have a couple of oxidation states that are actually stable. The fact that carbon can go all the way from a -4 to be anything between a -4 and a +4. Literally, carbon can have any oxidation state between -4 and +4 is what allows the citric acid cycle to work. What allows the electron transport chain to work is the fact that we can start with something where carbon is fully reduced, and we can basically take those high energy electrons away from it a couple at a time to give them to oxygen. Because oxygen's really unstable on its own. When oxygen is O2, oxidation state is 0, right? But oxygen's really electronegative. So these O2 molecules really want to grab electrons and become oxides, to become a -2 oxidation state. And so what our body does in the electron transport chain and in the citric acid cycle is it takes these high energy electrons from carbons and hydrogens, feeds them to oxygen, and in the process generates ATP. So the electrons basically start from their least stable state, and over a bunch of steps, every time you make a step on the electron transport chain or on the citric acid cycle, it's going to get a pair of high energy electrons that can make an ATP. If we only had 2 possible oxidation states for carbon, that wouldn't work. Right? Carbon works really well for this, and where other elements don't, because it has a bunch of intermediate steps along the way. All right. Last definitions before we take our break here. I'm not going to forget break today. Once we can figure out what's being oxidized and what's being reduced, we also figure out what's called the oxidizing agent and the reducing agent, which is basically just another way of looking at the same thing. The word agent means it acts on something else. In general, in any case, a secret agent acts on another country's interests, for instance, I guess. That, for whatever reason, I watched a lot of Bond movies when I was growing up. When I hear agent, I think secret agent. Agent just means it acts on something else. So if it's a reducing agent, it's causing something else to be reduced. If it's an oxidizing agent, it's causing something else to be oxidized. You see, it really is using the same definitions, but we kind of flip them backward. So what is being oxidized in this case? What's going from, I guess let's start by just doing the oxidation states here. When you put sodium in water, you make sodium hydroxide and hydrogen gas. So sodium starts out as, let me switch colors. So sodium starts out as a 0. What is sodium over here? Well, if we know that's hydroxide, we know that's a sodium ion, right? Sodium ions have to be +1. So is the sodium oxidized or reduced? It lost an electron, but the charge went up. So remember, lose electron is oxidation. Leo says GER. So the sodium goes from 0 to +1. It's oxidized. So there's our oxidation. What's the oxidation state on the oxygen before and after? Water, we've done that one a bunch of times, but just for practice, oxygen's the most electronegative, right? So it's got to be a -2. What about over here? The entire hydroxide is -1, but the oxygen is still -2. The oxygen's still the most electronegative thing here, right? So it still has first dibs. It's still -2. So the oxygen didn't change. Oxygen was neither oxidized nor reduced. It's there, but it's not changing oxidation states. So what's our only other option? Hydrogen. This hydrogen we know is a +1 still, so we've already done that. Those are +1. What's our oxidation state on hydrogen gas? Neutral. So some of the hydrogens go from a +1 to a 0. To do that, did they gain electrons or lose electrons? They had to gain electrons to go from a positive charge to 0. They had to gain electrons to reduce the charge because electrons are negative. And this is where it helps that we really established early on electrons are negative. We worked a lot with charge because it's counterintuitive. To gain something and your charge goes down. That's the way it is. So our reduction reaction here is the hydrogen in the water turning into hydrogen gas. So when it says what is the oxidizing agent, what is the chemical that causes the other compound to be oxidized? So the oxidizing agent is whatever is getting reduced. And sodium then is the reducing agent. I keep trying to spell agent with a Q. All right, so it seems like superfluous. Why would we need that? It comes in handy when you start taking more science classes because, and again, I always go back to OChem as the example because it's the other class I teach where we use this all the time. In OChem, we care about the carbon-based compounds, and then we've got whatever else there is. So if we're talking about trying to reduce a specific carbon-based compound, we say, well, we use a reducing agent. Doesn't necessarily matter what the reducing agent is, we just need something we can put with it so that the carbon gets reduced. So it's really more of just a linguistic thing. When you get to different classes, we'll use the term oxidizing agent versus reducing agent as a way to keep things straight. If you're going into allied health fields, then probably the only place you're likely to see this in the future, other than maybe a biochem class, is going to be on the TEAS test or whatever the standardized test is for your profession of choice, is probably going to have this as a vocab term when you do your studying for those standardized tests. you'll see this again. It really is most useful if you're going into either chemistry, physics, or engineering. We use these terms a lot. All right, let's take our break. Let's come back at 11:30. And we'll do a little bit more practice with this, and then we'll start talking about acids and pH.
Benjamin Neighbors. Yeah, that's about, or three, you can have four.
Correct.
So do we attach like instantaneously? There's no stepping up in that?
So you're asking about what's called mechanism. I don't know my inorganic mechanisms that well off the top of my head.
Okay.
So there's probably more than one way you can do it. It's what can happen with mechanisms is you can sometimes make something that's unstable very short-lived. So it's possible that PCl4 does exist as a step on its way, but it's not going to be the way we define whether or not something is stable enough to be considered its own compound is can we isolate it? If can we stop the reaction in the middle and just get the intermediate? And that's the one I'm fairly certain you can't do that.
Thank you.
Sean,
Yeah.
my dad texted me and said, hey, is it okay if I come up a day early? And,
Okay.
would it be okay if I do the Wednesday lab so that I can be there and run into my house this afternoon?
Yeah,
Okay.
yeah, absolutely.
Do you want me to send you a message so it's in writing?
Send me a message. We haven't had a super full labs on Wednesday, so it should be fine. I guess technically, I can't guarantee
Okay.
Wednesday, but the very worst case scenario, you
Okay. If it's super packed Wednesday, I'm happy to come back.
Okay.
Thank you so much for.
Yeah, no worries. That time on Thursday has been so helpful for a lot of students that we're trying to do that. We're trying to make something institutionalized where we always have like a makeup lab. Because it's really helpful.
Wonderful.
Yeah,
So,
I agree.
thank you so much for being so accommodating for us.
Absolutely.
We're trying to get this to be something standard.
Absolutely. We're always trying to do better here.
Hell yeah.
All right, as everybody else is coming back, we'll start reminding ourselves how concentration units work. So the solubility of sucrose in water is 2,000 grams per liter. What is the molarity of a saturated sucrose solution? if you can dissolve 2,000 grams per liter, how many moles per liter is that?
Yeah, so I'm calculating. Yeah. I'm on the right track.
So we know we can dissolve 2,000 grams of sugar in 1 liter of water. Getting the molarity just means we need to know how many moles of sugar we can dissolve. So if we have 2,000 grams, we just need to convert that to moles. So we need the molecular weight, which is 342 point something.
2948.
2948. Although we do, depending on, you might get that 10,000ths place, depending on if you're using the mass for hydrogen. But our carbon only goes to the 1,000ths place, and our oxygen only goes to the 1,000ths place. So we're just going to round it to 5 at the end. So if we know we have 2,000 grams per 1 liter, and every 342.295 grams is 1 mole, we get right. So as a reminder, in chemistry, our concentration, the concentration units we want are almost always moles per liter. We do see stuff like grams per liter or percent by mass sometimes, mainly just because that makes it easy to make a solution. If you have concentration written like this, because I can just go way out 2,000 grams of sugar and put in 1 liter of water. So, but it doesn't help me if I'm actually going to do any stoichiometry with it. So chemists, you might see concentration units like this in, I'll blame biology. Biology is really bad about this. They pretty much always are going to put their concentrations in whatever makes it easier to make the solutions, even if it doesn't make sense in terms of then doing calculations with that. So in chemistry, we are always going to use moles per liter. All right. Let's talk about these precipitation reactions a little bit more before we get into acids and bases. So if we have a solubility table, we actually can predict the products for these ones pretty easily. Like I said, it's not on the final, but it's still worth practicing so that you know a little bit about how these solubility tables work. because I actually do think it helps you identify the precipitation reactions too. So sodium nitrate and potassium chloride. When we mix those two together, what are our two new combinations? Sodium can't form a compound with potassium ions because they're both positive, right? And nitrate can't form a bond with chloride because they're both negative. So if we started with potassium or sodium nitrate, we could make sodium chloride. And our other possible combination is potassium nitrate. Are either of those going to be solid? Are they either of them going to form an insoluble compound? Well, we know that sodium chloride won't because we know what that is, right? So potassium nitrate, we still might want to double check. We still want to double check this too. Sodium chloride, sodium's on our list of soluble with very few exceptions. So that one's going to stay aqueous. Guess what else is on our list of soluble with very few exceptions? Both nitrates and potassium. So when we mix these two solutions together, we don't get anything that's going to turn solid. Right? When we mix these things together, we had sodium ions and nitrate ions floating around, and we had potassium ions and chloride ions floating around. We still have everything still just floating around. So what that tells us, so we actually don't have a reaction. There is no reaction because when we mix these together, nothing happens. Right? These are our two possible compounds, but they both are still soluble in water, so we just leave it. How about sodium chloride and mercury 1 acetate? We know sodium is going to be soluble with everything, right? So we know we can write sodium acetate and acetates are soluble with very few exceptions. So both sides indicate this one's going to stay soluble, stay aqueous. Our other possibility is mercury 1 is a weird ion in that it doesn't split up by itself, so you actually can't have Hg plus 1. If you have mercury in a plus 1 oxidation state, it'll naturally form a weird polyatomic ion. It looks like that. So don't worry about that at this point, other than the fact that it shows up here and I'm writing it out for you. You don't need to worry about that for now, but that's why it looks funny. Chlorides are soluble. Chlorides, including chlorates, perchlorates, bromides, and iodides, are all soluble almost all the time, except for 4 exceptions. One of which is mercury 2. Sorry, it's mercury 1, Hg2. So chlorides are soluble except for these, which means it's insoluble. So this forms a solid, it forms mercury 1 chloride as a solid. So this would be our reaction. All you do for precipitation reaction when you're mixing two aqueous compound or ionic compounds, switch the cations and see if you made something that's insoluble. That's all there is to it. Just takes a little bit of practice to get the hang of the language. And insoluble means it turns solid when you mix it together. All right, how do we feel about these? If I gave you this table in a page of these, you feel like you could complete them? All right, main question when it comes to the test for a week from Wednesday is, if I had that written out, could you tell me it was a precipitation reaction? Because that's the way it shows up on the test for this class. Right, so 2 aqueous solutions that are ionic solutions, and then you end up with a solid at the end, and nothing changed oxidation states. Oh, don't know what happened there. This is just a different example of what a solubility table can look like. Sometimes it actually will just show you all the possible combinations, and you get something like this. Green is soluble, red is insoluble, yellow is slightly soluble, because it turns out solubility is kind of more of a spectrum than it is binary yes, no, like most things in science. So for instance, if we're using that to answer our same question from before, and this one doesn't have mercury on it, but if we looked at the strontium sulfate, we were checking strontium sulfate for number 3. We'd come over here, and again, it doesn't have strontium on there either, but it does have sulfates. Normally we'd say, okay, sulfates, they're almost all soluble with a couple of exceptions. Strontium is probably soluble. I go back 1 page though, or more. I don't know what happened with that one. Sulfates are soluble with these exceptions. And so we just, very careful reading, find one of the compounds in your solubility rules, see what it tells you. All right. Couple more vocab things. If we're trying to actually show what's going on in these precipitation reactions, a lot of times what we actually want to see is the individual ions all split up. Right, so this is what's called the molecular form, or the molecular equation, where we write it out like it's regular ionic compounds, aqueous versus solid. But we learned last week, or maybe it was, yeah, I think it was last week, last Monday, we started talking about how when you dissolve ionic compounds in water, they don't stay as an ionic compound. When you put lead nitrate in water, it doesn't stay as lead nitrate. It really turns into lead ions and nitrate ions, all surrounded by water molecules that make them all more stable. So the ionic equation for these reactions basically just says split everything up. If it's aqueous and ionic, break it up into its pieces and write it that way. So this is the same reaction written in molecular form versus ionic form. This is kind of a lot of writing. It's a pain. The only difference is once you form a solid, you do write it in its normal molecular formula. But if it stays dissolved, you just leave it as aqueous. So we had nitrate aqueous over here. We still have nitrates over here. We had potassium ions over here. We still have potassium ions. This last form is the easiest way to do it. Basically says anything that doesn't change, you just leave it off. So the net ionic equation, or net ionic form, just says, okay, if it shows up both as a reactant and as a product, it didn't really do anything. If it didn't really do anything, why bother writing it in your equation? So the net ionic equation just subtracts everything that's not changing and removes it from both sides. Right, so again, same reaction. We just leave off those counter ions because they're not doing anything. We leave off the potassium and the nitrates. And again, based on our Snowmageddon week, normally I have a whole assignment where I make you write out a whole bunch of these. Practice doing precipitation reactions and writing them in all three forms. It doesn't show up on the final, it's not that relevant, but I want you to have heard the terms, because thinking about ionic aqueous solutions like this is really helpful in the future. And it's really common in medications too. Anytime you see something as a salt or as a hydrochloride as a medication, that means that basically you've got something where you've got chloride. It says the hydrochloride salt, that just means that you've got chloride there to balance the charge, but it's not doing anything. In other words, it would show up in the total ionic equation, but not in the net ionic equation. You may think of something that's prescribed as the hydrochloride. You see it mostly from pharmacies. They don't really put it on packaging other than in like the nutrition or the drug facts on the side if it's over the counter. Adderall. Adderall is amphetamine salts. Amphetamine's molecule looks like looks like this when it's in water. It's got this plus charge there, so it needs something to balance out the charge. So amphetamine hydrochloride would be both of these put together, but when we actually dissolve it in water, when you actually put it into your stomach, it splits up and you get this version, this molecule, and then this ion that's just there to balance the charge. Right, so thinking about these things as when they're in solution, they become separate pieces, winds up showing up a lot in biochemistry. In fact, biochemistry notoriously gets really, really lazy with balancing out the charges, because why bother even writing that? We don't care about it. That's what's actually going to change things in the biological system. So ignore that, because there's just always some chloride around. I don't think they actually prescribe Adderall as the chloride. I think they prescribe it as the sulfate salt, but that's beside the point.
Does that mean you can take a net equation and just add anything that will balance it and come up with the same result?
Basically, it's a good question, because it doesn't really matter that it's potassium iodide. If I was trying to do this reaction in the lab and I didn't have potassium iodide, but I found sodium iodide should work just as well, because it's still got the iodide, and I'm still not going to make something else that's not going to dissolve, right? So yeah, that's one of the reasons why we do it, because it doesn't matter what the iodide is for the most part. Lithium iodide would probably work too. Calcium iodide would probably work. There's lots of options as long as we have the iodide, because that's what's in the net ionic equation. Now, if you're not careful, you might wind up with other reactions happening. It's possible to get a precipitation reaction where you get two solid products if you're not careful about what you're mixing, in which case you're going to get not just one product at the end. You actually wanted to save that and filter it out for some reason. You would get a mixture of two different solids, which then is its own headache to try and separate two solid powders from each other. But it means the reaction will happen with pretty much anything. Right, and then I do also want to, the whole idea of slightly soluble, turns out everything dissolves in water a little bit. It just might be a really, really small amounts. If I go back to our sucrose example, sucrose, you can dissolve 2,000 grams in a liter of water. That's a lot of That's 4 pounds of sugar in a liter of water, right? Because a kilogram is about twice a pound. On the opposite, so sugar is very soluble, but even sugar has a maximum. You can't become more saturated than about this number. Something like silver chloride is going to have a solubility in water, but it's going to be like, I want to say it's like 10 to the minus 7 moles per liter. It dissolves in water very slightly. Might be enough though that it still matters in terms of water quality testing, because some heavy metals, for instance, like silver, if they're present in our water, even in small amounts in the parts per million range, can still be toxic over time. So just because we say it's insoluble, we mean it's insoluble within sig figs, basically. It doesn't mean that none of it dissolves. It means very, very tiny amounts of it dissolve. And if that's interesting to you, then you should take general chemistry, because we spend a full 3 weeks on 4 weeks, 6 weeks, 6 weeks probably on equilibrium, which is reactions that happen a little bit, but not all the way. All right, let's do stoichiometry with a precipitation reaction. Does it matter that it's precipitation reaction when it comes to figuring out limiting reactant? Not really. We've got 25.0 milliliters at 1.20 moles per liter. And we have 15.0 milliliters at 0.900 moles per liter. And then we have an actual yield down here. If we look at this is balance, figure out limiting reactant, calculate theoretical yield, then get percent yield. We're doing all the steps for this one. Give you a head start. After we balance the reaction, what's our first step to answering any of the rest of this? Stoichiometry means our first step should always be put everything in moles. We just have to do it using concentrations for these ones now because they're solutions. We're in milliliters and we want to use molarity to get to moles. We need to get to liters first, but that's an easy conversion. 1,000 milliliters is 1 liter. Then we can use our molarity as a conversion. Because remember, capital M means moles per liter. So we can say, okay, for every 1 liter, I get 1.20 moles of KCl. be able to do a quarter of 1.2 in my head, but it's Monday. Because I didn't give myself a ton of room here, I've got to erase that. We do the same steps, 15 mils and 0.9. I think we get 0.0135. And then how do we get our grams of barium chloride actual into moles? Check your units. We're in grams, right? We're in grams of a solid, we can just use molecular weight. So what do we get for that number? $2.45 is going to turn into 0.2. Give me one more sig fig.
Sorry.
117. Perfect. Because that 0 doesn't count as a sig fig. Common mistake. Remember, just because it's after the decimal point doesn't mean it's a sig fig. A leading 0 is anything that's left of the first non-zero number. I did tell you at the very beginning of this class, when I first learned sig figs, it was going to be the one thing that I knew without a doubt it's going to be the number one thing I mark you down for. Not in terms of total points necessarily, but it's really easy to mess up. It takes a lot of practice to get good at sig figs. All right. How do we know it's going to run out first? We're using the potassium chloride up at a 2-to-1 ratio, right? So we can eyeball this if you can do doubles in your head. If we're using this up twice as fast, do we have more than twice as much of the barium nitrate? Twice as much of the barium nitrate would be 2.027, right? We have more than that. If the logic is still, if you're not able to do that in your head, the better option is to show your work anyway. In fact, on a test, I would prefer you to show your work. We should this is just our reasonableness check. Because we have less than half as much barium nitrate, I'm pretty sure we're running out of that first. If you're not sure, it doesn't matter. Pick one of these, see how much product you can make in terms of moles. And then do the other one, see how much product you can do in terms of moles. So 0.135 moles barium chloride. For every 1 mole of barium chloride, that's 1 mole of barium nitrate, not chloride. So 1 mole of barium nitrate means we get to make 1 mole of barium chloride. Versus 0.0300 moles of the potassium chloride. And for every 2 moles KCl, that's 1 mole of barium chloride product. Versus 0.0135. We can't have, these can't both be true, right? So whichever one is less, that's our actual theoretical yield. And that also tells us our limiting reactant. This has to be our limiting reactant because that's the reactant that makes less product if we use it all. Bro.
So that's your that's 0.035.
Exactly. Right, we can't just say I have less moles of barium nitrate, therefore it's running out faster, or that therefore it's going to run out first, because they're not being used up at the same rate. Right, so if it's a simple 1-to-2 ratio, you might be able to guess right if you get nice clean numbers like this also. You still want to show this work, especially on the test. One, because don't trust that you're doing your mental math properly in your head. Show the logic for it, so that at least that way, if you're wrong, I can give you partial credit for it. And 2, you might catch yourself. There's times when I expected something different than what I actually got. It's easy to make mistakes when you do mental arithmetic, right? Our mental arithmetic is a good way to check that our calculator input makes sense, but we don't want to rely on it entirely. Especially not on a test. All right, so there's our theoretical yield. What's the percent yield? So percent yield is actual over theoretical times 100. The part divided by the total, just like a grade. If you know that there's 135 points possible and you actually scored 117 points, getting your grade is you take what you actually got divided by what you might have gotten times 100. So should get something in the, what does that wind up being? Close to 90%.
Yes. Price.
There we go. See, I told you we'd get better at these. Right? They still seem like a lot when it's a blank page. You start biting off a little bit at a time. All right. In the 20 minutes we have left, we're going to talk about acids and pH, and then I'm going to run you through some practice pH problems at the beginning of lab. So our acid-base reactions, acids can be defined a variety of ways depending again on what context you're using it. The first definition of an acid was it's basically anything that if you dissolve it in water, it increases your number of H+ ions. That's sort of an old school way of thinking about it. This Arrhenius is one of my all-time favorite scientist first names. His name is Svante. Svante Arrhenius from Sweden. came up with this idea of saying, okay, whatever you dissolve, if you dissolve something in water and it increases your amount of H plus ions, that's an acid. That's not a terribly useful way to think about it when we start talking about in terms of molecules, but we'll cut him a break because this was in like the 1880s he came up with that. So he did pretty good for the tools he had, considering covalent bonds had not been even hypothesized yet. Number one definition we're going to use is this Bronsted-Lowry definition. Anytime you can give away an H plus, which in acids, they often just call an H plus, they'll just call it a proton, because a hydrogen atom is a nucleus with one electron, right? So a hydrogen ion is just the nucleus, and the nucleus of a hydrogen is just a single proton. So sometimes we'll see them referred to as a proton donor. It doesn't mean we're actually changing what's in the nucleus of other atoms. It just means we're moving an H plus around. And then this last one shows up more in higher level chemistry, a Lewis acid. Means it's an electron acceptor. I want you to be aware that these three definitions exist, but for the most part, that's the one we're using. Right, whatever gives away an H plus is an acid. Whatever accepts an H plus is a base. So just like redox reactions, you couldn't have oxidation without reduction. With acid-base reactions, you can't have an acid give away an H plus unless there's something around to accept it. So our acid-base reactions always include both an acid and a base. The Arrhenius definition of a base looks a little bit weird, but it'll make sense when we define pH in a few minutes. An Arrhenius base is not, so if we think about acids as being opposite of bases, an acid increases the concentration of H plus ions, and a base increases the concentration of hydroxide ions, not H pluses, which is a little bit weird. Unless you know how H pluses and hydroxides interact when we're talking about water. When we're talking about water, well, hang on a second. We'll practice talking about acids and bases first. So if every reaction requires both an acid and a base, whatever gives up an H plus is the acid. Whatever accepts the H plus is the base. So if this is our reaction, does it look like, for starters, does it look like a precipitation reaction? If we're trying to classify this, we use solid. There's no solid. We did start with mixing some stuff together, but we didn't make a solid, so it's not precipitation. If we're trying to figure out if it's a redox reaction, we would then go through and we'd assign oxidation state to everything. We'd see nothing changes. In fact, we already did something look really similar to this with ammonium and ammonia, right? So that's a pretty good indication that if it's not a redox reaction, it's not a precipitation reaction, it's probably an acid-base reaction. So what's acting as the acid? What's giving away an H plus? Yeah, we started with H2O and then we took an H plus off of it to make hydroxide. So that tells us that the acid in this reaction is the water. Water is acting as an acid in this case. We don't name it like an acid, but it's behaving like an acid because it's giving away a proton. Which means The ammonia is our base in this case. It started as NH3 and turned into NH4 plus, so it accepted an H plus ion. If it accepts a proton, it's the base. Right, so anytime you have a reaction drawn up and you're not sure if it's an acid-base reaction, see if you can narrow it down to say, okay, there's my acid because it's turning from H2O to hydroxide. It lost an H plus. If the reaction happened backwards, so if the ammonium went back to being ammonia, is that acting as an acid or a base? That would be an acid, right? So if I rewrote it from left to right, the way we like to write things, the ammonium would have to lose an H plus to do that, right? So whatever acts as the base first, if it happens backwards, that's going to be the acid. So we call that the conjugate acid. So whatever the base is turns into the conjugate acid. Conjugate acid is always the result of this acting as a base. If ammonia accepts an H plus, it always turns into NH4 plus. So we call this the conjugate acid of ammonia, which means hydroxide is what? If the reaction happened backwards, hydroxide would be the base, right? Conjugate base.
Is it called that because you can chain these reactions together with other?
And it means that the other thing it means is that you can kind of split this into two reactions. We have ammonia acting as a base, and we have water acting as an acid. Water acting as an acid always gives the same conjugate base. Ammonia acting as a base always gives the same conjugate acid. So it kind of creates these pairs where NH3 and NH4 plus are always linked together by just a single acid-base reaction. All right, we already talked about naming these. So I'm going to skip through this part. What would be, if we did name water as an acid? The conjugate base would be hydroxide, right? So if you took hydroxide and you added enough H pluses to make it neutral, you'd get water. When we name anything that ends in "ide," so we could name water hydrogen hydroxide, right? Because we added an H plus onto a hydroxide. If it ends in "ide," when it's an acid, we write hydroic acid. So just like people that are really a pain or playing a joke on you could call water dihydrogen monoxide. Have you ever seen those like joke signs? Beware of dihydrogen monoxide. 1 teaspoon can kill you. Maybe that's just something people send me because I teach chemistry. But there's lots of like beware the dangers of dihydrogen monoxide stickers out there and things like that. We're going to name water as an acid, be hydroxide, hydrogen hydroxide, so it would be hydrohydroxic acid. You could also talk about the dangers of hydrohydroxic acid too. That sounds really nasty. Sounds like bad stuff. Except we know better. All right. This is the other one I want to talk about. When you put water in water, water can act as an acid towards itself. Not only can water act as an acid towards itself, it can act as a base towards itself. So if you put, I'm just going to color code these two together, one of your water molecules can give away an H plus. One of your water molecules can accept an H plus. Which one is acting as the acid, red or blue? Blue. The blue one lost an H plus, that's why it turned into hydroxide. So this would be the conjugate base. The red one is acting as a base. So H3O plus, which we learned the name of that on our polyatomic ion sheet, right? Is the conjugate acid. If you don't remember, that's hydronium. So if this can happen constantly in pure water, do you ever actually have pure water? Even if you put it through a reverse osmosis filter, got all of the minerals out of it completely, made it completely deionized water, it's not actually 100% water molecules still. Because this happens anytime you have a system of water, you have water acting as an acid and a base towards itself. This is what this ability to be either an acid or a base is. It has a specific name. Amphoteric, I believe. Helps if you can spell that. An amphoteric substance is anyone that can be either an acid or a base, depending on the situation. Sometimes they're also called amphiprotic. Protic from proton, because we can move a single proton either way. And amphi, like amphibian, means either direction, like ambidextrous. So what does that mean? Other than, well, we can't ever have pure water? It means that under normal circumstances, when we always have a small amount of this, it's not like this reaction happens completely. It actually stops halfway, not even halfway. In fact, it stops so quickly that we basically can treat these concentrations like they're almost zero. Because in equilibrium, when this reaction is done happening, when it's happening as much backwards as it is forwards, the concentration of hydroxide times your concentration of the hydronium. So hydronium is more accurate, but sometimes we just say it's the same as an H plus. If you put the H plus in water, you get hydronium. And this is the way that the pH scale is defined initially. And so you still see it written like this sometimes, but it means the exact same thing as H3O plus. We're talking about in a water-based solution. This reaction stops when these two concentrations multiplied together are equal to 10 to the minus 14. This constant is called Kw. Kw is basically water at room temperature will always stop this reaction when these two concentrations multiply together, give you the same number, give you 10 to the minus 14. That actually winds up being critical because our definition of pH and acidity is based on that number. pH is defined as the negative log base 10 of your H3O plus concentration. So if you know this number, you also know the pH of the solution. This also means, though, if we're in pure water, what can we assume about these two numbers relative to each other? If it's pure water, are we going to have more of either of these than the other? No, because every time you make a hydroxide, you have to also make an H3O plus. So if these two numbers are the same, let's call it X, we get X squared equals 10 to the minus 14. Which then means, so if X squared is 10 to the minus 14, we take the square root of both sides, we get X is 10 to the minus 7. If your concentration of H3O plus is 10 to the minus 7, and you plug this in here, everybody's had a class that involved logs before, right? You don't have to have liked the logs. I just don't want to teach logs from scratch because I'm not a math teacher. If you take the log, take your calculator out, do log of 10 to the minus 7. What do you get? Minus 7, which with this negative sign in there. So the pH of a neutral solution is 7, which is something you've probably heard in other science classes or in high school at some point, right? 7 is neutral on the pH scale, might have been the way it was framed. 7 is neutral on the pH scale in water because that's when these two numbers are equal to each other. If you're at a pH of 7, that means these two concentrations have to be equal to each other. Whatever they are, they're going to be equal to each other when the pH is 7. All right, so lab today is going to be more practice with pH. And we're basically going to use pH to measure a concentration instead of starting from a concentration to get a pH. And then we'll do more practice with pH and calculations on Wednesday. And that's your last major skill is here's an acid-base reaction. What's the final pH? Okay, so I'll see most of you in the lab. And if I don't see you today in lab, I'll see you on Wednesday.